Now, in this particular case, I have a system of 3 equations but not 3 unknowns, right? If you count the variables, I have x1, I have x2, I have x3, I have x4. That's going to be 4 variables or 4 unknowns. So I have more unknowns than I have variables. And in this particular case, you can see that it's not a triangular system, right? It's not a perfect triangular system because to be a triangular system, those leading coefficients, I have to go down 1 over 1, down 1 over 1. But in passing from the second to the third equation, I have to go down over 2 to find the first non-zero coefficient. This is going to be called an echelon form. So the next best thing to a triangular system will be an echelon form. And echelon is a little more general because we're always going down and over, but I can go over by more than just 1. Does that make sense? Also, I should also mention these are called the leading variables, right? And I think tomorrow we're gonna look at this from another point of view, and I'll be calling these pivot positions. But these are you can see that x1, x2, and x3 are leading variables, okay? But because we went down 1 and over 2, x3 is not a leading variable. Oh, sorry, typo. That's x1, x2, and x4. My bad. Are leading variables, but x3 is a free variable. That make sense? And so for this reason, if I do the back substitution like I did with the triangular system, here it's going to kind of unfold in a different way, okay? So I'll show you what I mean. So using the method of back substitution, I can see that x4, if I divide the third equation by 3, so, or in other words, multiply the third equation by 1/3, x4 is equal to 3. And from that, I can back substitute into equation 2. And I can now see that x2 minus x3 plus 2 times 3 equals 5. Now, when you have a free variable, like x3 is a free variable, I'm going to introduce, this might seem like semantics, but I'm going to give it a name. I'm going to give it the letter T. This is a parameter, right? You know, in calculus 3, you would have used parameters a lot, you know, for parametric equations and that sort of thing. I'm going to regard x3 as a parameter because x3 can be anything, right? But whatever x3 is, that's going to automatically determine what x2 is. In other words, x2 minus t plus 6 equals 5. So whatever x3 is, call it t. You can see how x2 would be, well, 5 minus 6 is -1. Add t to both sides. I get -1 plus t. Or you could also write t minus 1. Does that make sense? So already I can see that there's going to be infinitely many solutions to the system of equations. Okay, let me take it one step further. I can go back to equation 1. 2x1 minus 4x2 plus 2x3 plus x4 equals 11. Can you see that? There it is. And now I can see what x4 is. what x3 is and what x2 is. Substituting back into my equation, -1 plus t here. That's x2. x3 is just t, and x4 is 3. And so now, again, depending on what the free variable is, that will automatically determine what x1 is as well. So 2x1, if I distribute the 4, I get, well, +4 minus 4t, is that right? Plus 2t plus 3 equals 11. I'm just going to push everything else to the right-hand side and solve for x1. So let's see here. I got 2 constant terms, 4 and 3. That adds up to 7. If I subtract 7 from both sides, and I also have a -4t and a +2t. That's -2t if I add 2t to both sides. I hope I didn't skip too many steps. Let me know if I made a mistake. But 11 minus 7 is 4. And if I divide both sides of the equation by 2, I get 2 plus t. So this is an example of a system of 3 equations with 4 variables, and it worked out that this system has infinitely many solutions. And what I have is, based on that one free variable, depending on what x3 is, that's going to determine what everything else is automatically. So that's what you'll be practicing in 1.1. It's going to feel like a little bit of pre-calculus review, but you're really going to try and, even if you're not used to it, try to get used to this method of elimination. And especially when you get to situations where sometimes a system of equations will have infinitely many solutions. We've even seen an example where a system of equations has no solution. And in the future, in the coming weeks, we'll be trying to investigate under what circumstances can I know whether there's no solution? Under what circumstances can I predict that there's exactly one solution? Under what circumstances can I predict there's infinitely many solutions? Will it ever happen that there's exactly 2 solutions? Things like that is where we're headed. And that's for any number, a system of any number of equations and with any number of variables.
Anyway, I have a question.
Yeah.
So with your echelon form here, where x4 is already given to you, does it matter if one of the variables is already given to you? Like, do you count that as a separate equation?
Yeah, you do.
Okay.
Yeah, and since you asked, like, notice what I don't have time to do this right now, but notice if I don't have that equation. Okay, now we've gone rogue. Okay, I have a new question that's being answered here. This is a system of only 2 equations, but I still have 4 unknowns, right? Because of the absence of that last variable, now x3 and x4 are both free variables. I think it's like example 8 in the book. It is an example where it has 2 free variables. And so x1 and x2 are going to depend on what each of those 2 free variables are. And so you get the solution to this system of equations would involve formulas that depend on both of those free variables.